All right, so the next definition we have is one that's fairly intuitive, and that is the definition of increasing, decreasing, and constant. So, decreasing, if you have two different x values, one less than the other, then a function's increasing if the value of the function f is uh, smaller at the smaller x value, and the value of the function f is larger at the second x value. So here, increasing. All right, this x value is to the left of this x value, and then the value of the function is less than here and greater than here. So this means it's increasing. If that is true for every single pair. So if you've got a graph, and no matter what two x values you pick, as long as one is less than the other, this is always true. And then we have similar statements for constant. The value of the function is the same no matter what two x values you pick. And now here, it's decreasing if, when you pick your two x values, one less than the other, the value of the function is bigger at the first x value and smaller at the second x value. So that is our decreasing function. So this word monotone, monotonicity. So a function is monotone if it is always increasing or always decreasing. So a function that sort of varies, like sine or cosine, or even just a cubic, or even a parabola, that function's not monotone. We might say that a function f is monotone on a certain, portion of it. If we just only look at half the graph of x squared, let's say, we could say it's monotone on the interval 0 to infinity, but it is not monotone in general. So we would say x squared is not monotone because unless you specify a more specific or restricted domain of the function, you always would assume the full domain, the largest domain possible, which x squared, its domain is all real numbers, and on all real numbers, the graph of x squared looks like this, which clearly is not monotone in the full thing. On half of it's monotone, the other half is monotone. So if you wanted to talk about monotonicity, you'd have to say is monotone, and then you'd have to say on, and you'd have to put a specific subset of the domain on which it is monotone. So this theorem here, the sign of the derivative, if we have a positive derivative for every x in some range of x values, then we can conclude that f is increasing. And if the derivative is negative, then we can conclude that f is decreasing. Again, think about this. The derivative tells us the slope of the tangent line. So if we know that on a graph, all of the tangent lines have a positive slope, then that means they have to be increasing. Take a look at example 3. Show that f of x equals natural log of x is increasing. So what we can do is use this above theorem here and show that the derivative is positive. So let's go ahead and take the derivative. The derivative of the natural log of x is 1 over x. Now 1 over x isn't always positive, right? Because I could plug in negative 2. And if I plug in negative 2 into the derivative, I'm going to get negative 1 over 2, which is negative. But here's the thing. We have to think about what is the domain of the original function. So if we graph the natural log of x does something like this. There's this vertical asymptote here, kind of. It just plunges downward. So the domain for natural log of x, domain is only the positive numbers. So because this function's only defined for positive numbers, the fact that its derivative is 1 over x, and sure, 1 over x in and of itself does have a domain of all numbers except 0, but because we are relating this derivative to its parent function, the natural log of x, and the natural log of x's domain is only positives, we can say that this is greater than 0 for all x in 0 to infinity, which is the domain of natural log of x. So by the theorem, ln x is increasing. And we don't have to say increasing on 0 to infinity. We can just say is increasing, because when you only say this but you don't specify something specifically, then you would assume that it's increasing on the domain of the function. And the domain of the function is this. So to state, if we were to add that on 0 to infinity, it would just be a little bit redundant. Not incorrect, just redundant.